Okay, so anyhow, logistic growth. Now, constant growth rate ain't logistic. Your y prime is simply equal to some k times y. Okay? If you have annual interest being compounded annually at 5%, k is 1.05. Okay? And if you don't know that, well, you're going to need to. Okay? Now, it means if it's population, if y is your population, and y has a 5% growth rate, then you have this thing here which is called your growth factor, which is your growth rate, which is 0.05 added to 1, because the 1 means you get to keep your population, and the 0.05 means you get to add that much. Okay? And you solve that, and your solution is y equals a e to the kt. And that should be real familiar to you. Okay? Okay, so that's constant growth rate. Now, logistic growth. Okay, you start with y prime equals ky. Okay? But, I need a little more room to write it out coherently. You got something in between here. Okay? It's some constant times L minus y times y. Okay, where L is your limiting population. So it's like you've got, okay, when I was a kid, actually, all the way into my 60s, my parents' best friends, they were like aunts and uncles, and the kids were more like cousins, and they had sons the same age as my brother and I, and we'd go to their house, and they always had in this alcove, as you go down to the basement, this tank full of guppies. You know what guppies are? Yeah, I think they're pretty common. Okay? And there's, a lot of guppies in that tank, because she kept the thing well fed, very regular with it, kept the water clean, did everything right, and there were always 1,000 guppies in that big old tank. Okay? Well, that tank only had room for about 1,000 guppies. If it had 1,001 guppies, one of them would have had to die. Okay? Or, when one of them died, then one of the eggs that hatched wouldn't get eaten. Okay? Something like that. Right? There's a limiting population in that tank. Okay? You put 5 guppies in there, and overnight you're going to have 1,000 again. Well, it might take a couple of months to build a population, but they grow fast. They build fast. They lay a lot of eggs, and if there's room for all the little ones to escape the big ones, then they lay a lot of eggs. Okay? Population grows very quickly. But the closer it gets to the limiting population, the more slowly it grows. And if you were to reach the limiting population, you'd have a 0 here. Y prime would be 0, your population would level off. Okay? Now, if you had 1,500 guppies in there, the population would again approach this. But L minus Y would be negative, right? If the limiting population is 1,000, you got 1,500, you got a negative growth rate, which means your growth is going to sort of exponentially decrease. Not exactly exponential because of this. Okay? But you still got the Y there, because the more you got, the more eggs get laid.
Is that like nature finding homeostasis?
Yeah.
Yeah.
Yeah. Now, it's an oversimplified model. Real ecosystems don't do this, but that guppy tank probably did. Okay? Assuming that there was always an optimal amount of food. Okay? Assuming no diseases. don't know, those guppies must have been awfully disease resistant because there were always 1,000 guppies in that, or whatever. I never noticed, you know, I mean, from the age of 5, you know, I kept track of the population density. Well, no, I'm lying.
It always
Okay.
looked packed.
Huh?
Always looked packed.
Yeah, yeah, so you get the idea anyhow, okay? So in any system, okay, a lake, and you're trying to grow bass, or pond, you know, if it's deep enough and cold enough, grow trout maybe. Does that all make sense? Okay, so how do you solve this equation? Okay, well, let's see, okay. Just to define. Okay, if y is a whole lot less than L, then L minus y doesn't change much. Like if L is 1,000, and y goes from, let's say, 5 to 50, well, L minus y would then change from 990 to 950. They say, well, that's a change of 45. That's a lot of guppies if you're hungry. Okay? Okay? I don't think guppies are very filling. I don't like fish anyway. Okay, so, yeah, there's a difference of 45, but the proportional difference, you're only talking about 4.5%, or maybe 5%, okay, of the population. L minus y doesn't change much proportionally, right? So it doesn't have a lot of effect on this, so you essentially have almost a constant number here times k times y, and when you have a constant number times y, it's exponential. Okay? So, I can say y prime is nearly the constant multiple of y so you have nearly exponential growth. Okay? Now, on the other hand, if y is close to L, let's say you're up in the 950 guppy range, okay? Then y can't change much. You know, y can go from 950 to 1,000, that's still only a 5%, roughly 5% difference. So I can say that if L minus y is a whole lot less than y, then y won't change much, because that means y is getting real close to L. Okay? So y prime is again nearly a constant multiple is, I won't say again, it's nearly constant multiple of L minus y. since y is about roughly constant, it's only L minus y that changes appreciably in a proportional sense, okay? So, you know, if y goes from 950 to 960, y only changes by about 1%, but L minus y changes from 50 to 40, okay? And that's like a 20% change, okay? So you only got a 1% change in y, 20% change in L minus y, so y is almost constant, but L minus y is now changing, and it changes drastically from 950 to 999. L minus y goes from 50 to 1, right? So you want to have the sense of those numbers and a sense of these proportions in order to understand how this works, okay? Now, solving the equation's no big deal. Now, some things you do with it, we'll see in a minute, okay? Because we'll solve it, okay? Let's say it's no big deal. You got to know how to solve an exponential. You know, y prime equals ky, but you've done that, okay? And you got to know the steps, and the steps here are very similar. The only difference is that when you do an integral, you got to use partial fractions, okay? So I warned you about that. One of those things I told you to review. If you didn't, well, get on it, because you're going to have to, okay? So, okay, so it's nearly a constant multiple of L minus y in this case. And what this means is that if you have, okay, let's say that here's your limiting population. If you start your population down here, then you're in the regime where y is nearly, L minus y is nearly constant. It's most of this, right? So you start off with something very much like exponential growth. If you don't know what exponential growth looks like, you'll take a real pre-calculus course. Okay, and learn what these functions act like, and go back and look at what your calculus course tells you about the things. Okay? You got to understand these functions. That's the whole, you know, pre-calculus is supposed to be a course in functions. And exponential is one that's absolutely clearly part of the curriculum. Doesn't get done right because people aren't ready to learn pre-calculus because we don't have good prerequisites and we don't use placement tests. Because it would adversely affect our graduation rates and our success rates. So you have success when you don't have success because nobody knows anything, or everybody knows much less than they should. Now there's counter arguments to that. Okay, it's not an airtight argument. Okay, but there's too much of that, I think. Okay, anyhow. So you got exponential growth, right? Now that starts to level off though as you approach this. Now you know, y has changed significantly. So you keep on going sort of exponential, but it sort of levels off. And then as you approach up here, you approach this by something that's very much like an exponential approach to the limit, okay? So that's what you look like. You call that a sigmoid graph. Have you seen that terminology, heard it? Okay. Okay. It's a near exponential increase here, and a near exponential approach to your limiting population L. Okay? So I'm going to say that from here to here, pretty darn close to exponential. Depending on how near you want near to be, this could go a little further, not quite as far. Up here, it's a near exponential approach to L, limiting population. And here it's, the two tendencies are fighting against each other. And when you have your inflection point, that's when you go from, that's where the two are kind of in balance, okay? And that's, of course, probably where L minus Y equals Y. So Y is 1/2 L. So when you're halfway up here, assuming you start at a very low population, I'm not going to detail that at this point, but you get the idea. Okay, so now the question is, how do you solve the stupid equation? Well, what kind of equation is this? Huh?
What kind of equation is this?
What kind of equation do we have here? Is it linear?
No.
No, it's not linear. Why is it not linear?
Because y squared.
You're going to get a y squared. Good. So it's not a linear equation, so you can throw that out. Okay? Is it a Bernoulli equation? Well, let's not worry too much about that. Because there might be a question, because you have a y squared over there, and that could be part of a Bernoulli equation. You don't have any, and you got a p of ty, so maybe you could do it as a Bernoulli equation. Okay? Now, do you love doing Bernoulli equations? I mean, you got to love it to some extent because it's pretty neat. And you get the whole thing of integrating factors and stuff like that, and it's kind of a neat little package. Okay? And you're going to be tested on it, so you got to love it. Now, okay? But what's the easiest way to solve this equation? What other kinds of equations have we seen? We got the linear, yeah, homogeneous, non-homogeneous, first order linear, okay? You got higher order equations, which we've seen, haven't formally studied in the book, and you know what to do with them, up to a point. You got separable equations, you got exact equations, you got Bernoulli equations. Right now, that's kind of your list. Maybe I left something out. But we're adding logistic equations to it, okay? You can test it for exactness, okay? What else? Well, you've absolutely got to see, the first thing you look at when you have an equation, you see if it's separable. You could write that as dy dt, divide both sides by this and multiply by dt, and all your y's are over here and all your t's are over there. The only t you got's a dt, okay? So it's clearly separable. And if you don't have a strong desire to see when equations are separable, you're going to limit yourself. It's the easiest if you can do the integral. And of course, that's the case with any of them. You almost always have to integrate some. Okay? So this is a separable equation. Okay, and I hope by the time we have a test, maybe about next week, probably first of the following week, you're going to want to know that. Okay? You're going to want to be strongly attuned to separable equations. Okay? Okay, well, okay, the equation is separable. Okay, so it's very clearly separable. We have dy dt equals k times L minus y times y. So dy over L minus y times y equals k dt. Right? So you integrate both of these. Well, how do you integrate this? This one's easy. This is kt plus c, right? How do you integrate this? Well, I'm not going to go into lengthy explanation of this because I know that this is one of the techniques that you got in calculus. If you want to go to Khan Academy or any place else and see how it's done, if you need to review it, okay. But it's simply you say, okay, you know that if you add two fractions like this to get a common denominator, your common denominator is going to be L minus Y times Y. Okay? And then your numerators are going to add up to whatever the numerator is, and that numerator has to equal 1 for all values of Y. Okay? And if you didn't understand all that, we are at 21 minutes and 8 seconds. So you go back to 20 minutes and you get to hear me say it again, and maybe you pick it up. I'm not going to belabor it because you're supposed to know it. And you're supposed to have done 100 of these problems so you know how they work. Probably haven't done 100. You haven't done at least 20 though. There's something wrong. Okay? Now, and no offense to my colleagues, both of whom are great, and I know who taught you these courses, and they got, good results. So if you didn't get it, okay, maybe they should have assigned more of these. Not sure what went wrong, because you're both smart people. But you can get this. Okay, so, end of digression. So you get 1 over L minus Y times Y equals A Y plus B times L minus Y over L minus Y times Y. I don't know who taught you your algebra, but if that's not totally obvious, I taught the algebra course. As well as your pre-calculus course, we're supposed to get it in your calculus course. So if it hasn't been reinforced many times, again, so be it. Okay, so this means well, now this triple equal sign means identically equal. It's equal for all values of Y. Okay? Well, this means that this has to equal 1 for all values of Y. But that can only be if A minus B is 0, because if A minus B is anything but 0, it's going to change with Y, and this doesn't. Okay? Now, I don't know how you learn the method or anything. Is it magic, or is there a reason for it? Yeah, there's a reason for it. Just because Y changes and A minus B ain't 0, this has got to change, and it doesn't. So, A minus B is 0. And B, L equals 1, so B equals 1 over L. Thus, A equals 1 over L, because of course A minus B equals 0 says that A equals B. Okay? So now we can say that this is the integral of what? Well, it's going to be A over L minus Y plus B over Y. So it's I guess I'll just write the whole thing out. it's this, and because of this, A equals B equals 1 over L. And that equals KT plus C. Okay. Well, A equals B equals 1 over L means that A is 1 over L and B is 1 over L, so you're going to have just a 1 over L out in front of the integral of 1 over L minus Y plus 1 over Y dy equals KT plus C. Okay? Well, this means that 1 over L times negative natural log of the absolute value of L minus Y plus the natural log of the absolute value of Y dy equals KT plus C. So that the natural log of the absolute value of Y over L minus Y equals LKT plus C, where C being a constant absorbs multiplication by L. Okay? Etc. It means that Y over L minus Y is e to the LKT plus C. Okay? Now, I'll say that I'm not using the most elegant formulation of this thing. Your book does it a little more elegantly, but this is just brute force. Hit the net with a sledgehammer. Don't do anything tricky. And then you can see what your book does. It's not tricky. It just makes the notation a little simpler. Okay? Doesn't matter. It means the same thing, and you need to reconcile how it means the same thing. So I don't care if you imitate the book or imitate this. But by the end of it, make sure you see how they tell you the same thing. End up with the same solution. Do some of them both ways. Okay. Okay, so, well, that's all right. You know, all this is just a side note. That's Algebra 2. Late Algebra 1. It's taught right middle of the term, Algebra 1, I don't know. The rest of the world it is. So, we have this. So we want to fill in the et cetera, right? So again, just to repeat what I have there, natural log of the absolute value of Y over L minus Y equals KLT plus C. Okay? Put the K in front. I just feel better with it there. Okay? This means that Y over L minus Y equals E to the C, E to the KLT, which ought to look very familiar. And that equals AE to the KLT, where A is greater than 0. So that Y over L minus Y, and these steps ought to be very obvious because we've done them and used them and I've explained them, but if it's still a little fuzzy, which is not unlikely, reinforcing it, right? So this is in the form AE to the KLT, where A could be any number that's not 0. Since this is an absolute value, it could either be plus the AE to the KLT with A greater than 0, or minus E to the KLT with A greater than 0, which allows you to say that A can then be plus or minus. We don't have to worry about it. Okay? Well, then this says that Y equals L minus Y, AE to the KLT. I've said that A is not equal to 0, and I'm not going to bother to write it down in every step. It's probably a good idea if you do, though. Keep reminding yourself. Okay? And then we're trying to solve for Y, right? We've got a Y here and a Y here, it's hard to solve for. Well, we multiply through by this, and then we say, okay, Y times 1 plus AE to the KLT equals L times A e to the KLT. Right, we just, distribute this. We got a negative y times this, and add that to both sides and factor out the y, and that should be pretty obvious, okay? If it isn't, beat your head against it until, and go back, this is, let's see, this is at 30 minutes and 37 seconds. Boy, I'm getting long-winded in this. Okay, makes sense? I want to do it in detail, because my experience is people need to see it in detail, okay? Even though we've done something very similar with exponential growth, we want to lock it in. So the y then equals LAE to the KLT over 1 plus AE to the KLT. Okay? And of course, we could write that as then L times e to the KLT. I'm looking at e, but hopefully you know what that means. Okay? I guess I'll put the a in here. Okay. Now, I'm going to leave it in this form, although there's an advantage to dividing numerator and denominator by e to the KLT. Okay? And we might do that, but let's just look at this for a minute. So, what's the limiting value as t approaches infinity of this over this? Well, what happens to e to the KLT as t approaches infinity?
Approaches infinity.
If k is positive, which it pretty much is, it approaches infinity, right? And what happens down here? This one approaches infinity. So how much difference does one make?
Really?
It's, piddling difference, right? Which means that the numerator and denominator become almost the same, although the denominator is always a little bigger. One bigger. So when this is 48 quadrillion, this is 48 quadrillion and 1, so you never actually reach L. Okay? Intuitively, does that make sense? Now there's another way it could be written that also makes sense of it, in a little more formal way.